So that was a description of a set of potential features in a log linear tagger. This is just a recap on how log linear models then take features and produce conditional probability distributions of the form py given x under a parameter vector v. So we've already said that we have features f sub k for k equals 1 to m, and this gives us a feature vector. And recall that in log linear models we also assume we have a parameter vector v in r to the m. So if m equals 3, for example, we might have f x y is equal to 1, 0, 1, and we might have v is equal to 1, 2, 3. We can take the inner product of these two things, so v dot f x y is equal to 1 times 1 plus 0 times 2 plus 1 times 3, so that is equal to 4. And we can compute this inner product for every possible label in conjunction with x. So this conditional probability, as we described last week in the lectures on log linear models, is defined as e to the power v dot f divided by a normalization term, which involves the sum over all possible labels and e of v dot f with that particular label. How do we estimate the parameters of these models? Where do these v values come from? They typically come through learning parameters on a set of training examples, in particular using the regularized log likelihood methods we described last week in the class. So abstractly we assume some training set consisting of xi, yi pairs for I equals 1 to n. Then we choose our parameter values, v star, to be the v's that maximize the sum of two terms. So firstly I have the sum of log probabilities of my training examples, and secondly I have a negative term, so lambda is some constant which is greater than 0, dictating the relative weight of this term. And what I have here is basically the length squared of my parameter vector v, or more directly, as written here, the sum of squared parameter values. So this regularizer is going to keep parameter values small, whereas this term is going to encourage the parameter values to fit the training examples well. And as we said before, this regularizer term generally leads to much better generalization in cases where we could potentially have very, very large numbers of features. So concretely, in log linear taggers, our training set, these xi, yi pairs, is going to be a set of examples where each xi consists of a history, for example dtjj the red dog 3. So remember, a history consists of a pair of tags, the sentence, and the position that is being tagged. And each yi is going to consist of a part of speech tag. So we can take our training examples, our tagged sentences, and for every position in our training examples we can extract a history, and we can extract a tag, and we can use those history tag pairs as the training examples for training the parameters of a log linear model.